Alright, welcome to this video. It's about power and particularly rated power and rated voltage and how we can use those to predict what current products are going to draw and why we need to use certain things and not other things to make those sort of predictions. So first, what I've got here is a light bulb. This is a typical old incandescent light bulb. I'm using it because it's an example of the sorts of issues that you have when you're trying to work out what current a product or appliance in your house might draw. So let's have a look at it. You can see on the end it's got printed on it some stuff, and you might be able to just see that there now. It says 75W 240V. So that means that this has a rated power is 75 watts, and the rated voltage is 240 volts, which means that this bulb is intended to be fitted to a 240 volt power supply. Now in our main system we have alternating current, and the peak-to-peak voltage is significantly higher than 240 volts, but the RMS voltage, the root mean square voltage, which we'll learn about in level 3, gives you an equivalent the equivalent of a DC voltage of 240 volts. So there we go. So the rated power and the rated voltage. Now obviously I'm going to look at two different ways in which, theoretically at least, in which we could look at what sort of current then we'd expect this light bulb to draw. The first way is to use the rated power and the rated voltage. We can use power equals current times voltage, or voltage times current. It's not really a problem. 75 equals I times 240. I equals 75 divided by 240, and that is 0.3125 amps. Okay, so that's our starting point. That according to what's printed on the bulb, we could expect 0.3125 amps from this to be drawn if you connected this to a 240 volt power supply. Alright, that means if you have multiple of these in parallel, each one drawing 0.3125 amps, you would accumulate that current. For example, 3 of these bulbs in parallel would draw approximately 1 amp. Alright, the second way we could try and go about this, and we're going to compare these ways. The second way we might be able to go about this is we could look at the resistance of this bulb and then use Ohm's law. So we're going to just try that for a comparison. So let's go to our meter here. I've just turned it onto the resistance setting. I've got a nice close-up there for you so you can see what's going on. Okay, I'm going to contract. So on one of these 240 volt bulbs, this section here is actually an earth, whereas these two contacts are the two necessary contacts for the filament of the bulb. So let's have a look. Hold these on here nice and tight. Come on. I'm not managing to get a very good contact at the moment. Let's try again. Come on. Okay, here we go. I'm showing there on that meter, it says 107.9 ohms. 108 ohms. So we get R equals 108 ohms. Now, if I want to predict the current, I'm going to use V equals IR, and voltage. So the voltage is still 240 volts, equals the current times 108. I equals 240 divided by 108, and if I do that calculation, 240 divided by 108, I get 2.22 amps, which is, as you can see, something like 7 times the current that I got using the rated power. So what's going on? Well, to investigate that, what we're going to do is look at a 12 volt bulb. Yeah. Instead, because with a 12 volt bulb I can use this power supply here, and we can take some measurements while it's actually in use as well, safely. So here's a 12 volt bulb in a holder. Get a bulb back where I found it. Here's a 12 volt bulb in a holder. I'm going to take it out for a moment. We'll have a look at it. Now, I don't know how well you'll be able to see this under the camera, but marked right here it says 4W12V. So the 12 volt bulb has a rated power of 4 watts and a rated voltage of 12 volts. Okay, so this time, let's have a look. So firstly we'll calculate the expected current according to the manufacturer. P equals IV. 4 equals I times 12. I equals 4 divided by 12, which is 0.33 amps. Okay, so that's the current we expect this bulb when we expect to start flowing through this bulb if we connect it to a 12 volt power supply, so that this bulb sees 12 volts. If this bulb has 12 volts from one contact to the other, we should see 1/3 of an amp flowing through it. Right, so we're going to test that. But first, let's do it just as we did with the other one, thinking about what about if we looked at resistance. Okay, so set this back up again as a resistance meter. Now this one is slightly different to the other one. Instead of having 2 contacts on the base, it is just this, the shell of the housing here is one of the 2 contacts, and the other is the one in the center of the base. So contact that one and this one, and we get that this bulb has a resistance of 4.1 ohms. 4.1 ohms. R equals 4.1 ohms. B equals IR. 12 equals I times 4.1. I equals 12 divided by 4.1, which is 2.92 amps. Again, much higher than the current predicted by the manufacturer. So who's right? Well, let's fire it up into the circuit. So I'll put it back in its holder. Make life a little easier. Good contact. Right, now I've got to make my circuit up. So let's have a look. I want to make this one my voltmeter. Alright, got this one here I want to make my ammeter. So now I'm going to have, when I finish connecting this up, okay, let's have a look. Let's get somewhere where you can see all of the numbers and my predictions. So it's either the manufacturer is right with 1/3 of an amp, or our Ohm's law calculation is right with 2.92 amps. Okay, and we've got the current is going to flow out this blue one, through the alligator clip, through the light bulb, out through this blue one, into this meter, out through that blue one, back to the power supply. We're going to see the voltage on here. It's connected in parallel across this, so it's seeing exactly the voltage that this light bulb is going to see. And we've got our power supply here, which you can't quite see, is set on 12 volts. So we should get something like 12 volts. I think we'll get a little less because of the nature of this power supply not being up to much chop. So let's have a look. We turn it on, and what do we see? 11.3 volts. So measured 11.39 volts, and over here we're seeing 0. It's fluctuating a little bit, 11.36 volts and 0.2 amps it was at the same time, I think. So let's turn it off. Now we'll have a look. So what can we do with this? Well, firstly, let's have a look. The manufacturer thought it was going to draw 0.33 amps at 12 volts. Now, it only actually produced 11.36 volts, so we might expect the current to be a little lower. And sure enough, the current though is very, very close, or close enough anyway, to the manufacturer's rated current, or their expected current, and a long way away from the current we got when we just determined the resistance of the bulb and then used Ohm's law. And what power did it produce? Well, we can also work that out. Power equals I times V. 11.36 times 0.28, which is 3.18 watts. And we can also work out its resistance while it's actually running. So the resistance while operating, and we can use Ohm's law for that. V equals IR, R equals V over I equals 40.6 ohms. So its actual resistance while running there was 40.6 ohms, whereas when we calculated it based on its resistance while cold, or sorry, when we measured it using the meter on the light bulb, it was 4.1. And what is going on there? And the answer to that is Ohm's law works when the object is at a constant temperature. But of course, as we change the voltage being applied to the object from here, from the original, where it was just being held in space, right? There's no voltage being applied. The light bulb is cold, it's room temperature, which at the moment is reasonably chilly in my little workshop here. Its resistance was only 4 ohms. On the other hand, when it's running pretty close to its rated, or close-ish to its rated voltage, or when it has its rated voltage applied, it's running at the temperature that it's intended to be when it's operating, and suddenly it's actually 40 ohms. So a light bulb is an example of a resistor that is most definitely not being used in a way that stays true to Ohm's law throughout its scale. Every individual measurement could be made using Ohm's law. So you can work out the resistance at this higher temperature using Ohm's law. This is the true resistance of this object when it is at the high temperature. But to give you an idea, what we're going to do is we're going to hold this bulb here, and we're going to hold it over a nice background so that we can see as we change the voltages. So this is what this bulb looks like when it's having 12 volts applied and it's running more or less at its rated output. So it's a bright, almost white color. It's a slightly yellow white. Right, as we turn the voltage down, and you can see in this meter that we're now at 9.45 volts, and it's already become a lot less bright. So I turn it down again, 7.48 volts. You can't quite see it as easily as I can. It's now dropped right back to I can look straight at it. You can see how much it dips as we drop to 5.7 volts. Just under 4 volts. You know, it's now not much more than a glowing wire. Drop again, you can barely see it. It's only a very slightly glowing wire inside the bulb now. And so now, for example, at 2 volts, it's drawing still 0.1 amps. And if I work out its resistance now, resistance equals voltage divided by current. I've got 1.98 divided by 0.11. So its resistance has already dropped to 18 ohms from the 40 ohms we measured at full temperature. And of course it's still substantially above the room temperature in here, which is about 20 degrees. It's still glowing orange hot, so that might still be 1,000 degrees inside where that filament is. So it's still really hot where the filament is. It's just nothing like as hot as it is when it's glowing at that yellow white, which is several thousand degrees. So that is why we want to use if we're trying to work out what the predicted current for an item that we're looking at, how is it going to behave when we connect it in our household circuit, how is it going to contribute to the total current being drawn in our household circuit, that's why we need to use the manufacturer's rated power or the rated current they provide on the appliance, not go taking our multimeter and measuring the resistance of the product. Because any product that's got a heating effect, for example, and these are often products that have a high current draw or some of the biggest power users in our house. So heating elements. The heating element in a heating element heats up, and that means that its resistance changes as it heats up quite substantially. Similarly, other objects like electric motors don't behave in accordance with Ohm's law. If you work with an electric motor, next year we'll talk about inductors, and inductors provide a resistance or an effective resistance in a circuit, but they aren't. But if you measure it with a multimeter, you'll often see that there's almost no resistance there. But they still provide an impedance in a circuit. Otherwise, you get an infinite kind of current draw in your diode. So that's the trick here is that you can't rely on measuring resistance with your meter if the product either is going to have a high inductance or is going to have or is going to change temperature dramatically. In those circumstances, the resistance measured with your ammeter is not going to be representative of the resistance of the product or the impedance of the product in its use in the circuits in which it's going to be used. For that, you need to look at the manufacturer's rated power or rated current, and for that matter the voltage which they have intended it to be used with, and to only use it with the voltages that it's intended to be used with. For example, applying 12 volts to this light bulb, it won't heat up to anything like the extent it's expected to, and consequently its resistance will be much lower than expected. However, it's still not going to draw very much overall power. Okay, so that's the importance of rated power and the importance of rated voltage. Some products, of course, are provided not just with a rated power, they're provided with an actual indication of the current that the manufacturer expects that appliance to draw when it is connected to the rated voltage. You're able to use that instead, of course.